Okay, so because the limit from the right and the limit from the left do not approach values, but they increase without bound, then the limit as x approaches 2 does not exist. Now, you may see some people say here that the limit as x approaches 2 of f equals positive infinity. Some people might say that because the left and the right-hand limit both equal positive infinity, okay? Now, does that limit exist? No. If it equals infinity, it doesn't exist, right? It's not approaching a value. It is increasing without bound. But you can this tells you that it approaches infinity from both sides. Does that make sense? Because they just said the limit, it approaches 2, okay? So now let's take a look at example 2. Let's first look at the limit as x approaches 2 from the left. So as x approaches 2 from the left, let's start at 1. At 1, my function is 0. At 1.5, my function is 1. At 1.75, my function is about 1.5. At 1.999, and then 1.999, and then 1.999, what y value is my function getting closer and closer to as my x value gets closer to 2? It's getting closer to 2, right? Does it actually reach 2? No. This function never has a y value of 2. There's a hole there, right? Because at 2, what is the function value? -3, right? So here, f of 2 is -3. The actual function value at 2 is -3, but as we approach from the left, the function still approaches the y value of 2. So from the left, the limit is 2. And then from the right, when x is 3, the function value is probably up here-ish, 2.5, about here at 3, closer to 2, 2.001, 2.00001, getting closer and closer and closer to 2. What is my function value getting closer to? 2. So the limit from the right is 2. So does the limit as x approaches 2 of f exist? Yes. Why? Because both the left and the right-hand limits are the same value, right? They both equal 2. So the limit as x approaches 2 of f of x, we would say, is equal to 2 because the limit as x approaches 2 from the left of f is equal to 2, and the limit as x approaches 2 from the right of f is equal to 2. Try the last example on the next page on your own. So from the left, as x approaches 2, my function value is getting closer and closer to what value? To 3? What is my function value at 2? It is also 3, right? That's what that dot means, right? At 2, it equals 3. So here, the left-hand limit is the same as what the function is at that point, right? But from the right, as x approaches 2 from the right, my function's all the way down here. And what function value is my function approaching as we get closer to 2 from the right? -3. So does the limit as x approaches 2 exist? No, because the left and the right-hand limits are not equal. Can't write. It's been a long day. want you to think about this question in the box. If you want to refer back to examples 1, 2, and 3 to think about this question, it's saying, does f of a, so the function value at the point, have to be defined in order for the limit as x approaches that value a to exist? So think about that. You can refer back to questions, examples 1, 2, and 3. Yeah. Discuss with your table.
I describe it as no, because when you're saying the limit of x, or is it trying to what is it? So like
If there was a multiplier, then it would be, it would exist, but it would be undefined. So
yeah.
I'm gonna say it doesn't.
All right, let's look at examples 1, 2, and 3 together and just talk about this again. So we're trying to compare, does the function value have to be defined in order for the limit to exist, right? So for a question, example 1, is the function value defined? No. Does the limit exist? No. So both undefined and limit not existing. How about example 2? Is the function value defined? Yes. Does the limit exist? Yes, right? So here the function value is defined and the limit exists, but the question is, does that have to happen, right? Does that function value, does f of 2 have to be defined in order for that limit to exist? And then lastly here, we have the function value defined, but the limit not existing, right? So none of those really answer our question specifically on their own, but any ideas of a situation where we might have that case where the limit does exist, but the function is not defined?
Well, if you had a situation where you had a function that's defined at all points except for one point, because like x over like x minus 1 or something like that.
Yep.
And so then you could find the limit of that one.
And it would look similar, a possibility is similar to this one, but what would be different? No point at all, right? Just a straight up hole. That happens all the time, right? Like if you have, whenever those factors cancel out, right? Remember in a rational function, you get holes, okay? That is a hole. So is the function defined at all at that point? No, right? But the limit will exist because the function is approaching that hole, right? From both sides, okay? So that would be an example. So no, this does not have to happen. Here's an example of where f of a, if a is here, then here's a perfect example where f of a is undefined, but the limit as x approaches a of f exists. Like if this was 3, that limit would be equal to 3. Because from the right and the left, the function approaches the same value of 3, right? But the function itself is not defined at 3. So this touches on a really important point that you need to think about with limits. It does not matter at all what the function value is at that point. The limit could exist. It could not exist. It could equal a value. It could not exist at all, right? So the limit is the behavior, what's happening nearby, okay? It doesn't matter what's happening at that point, okay? Just what happens nearby in order for the limit to exist or not exist. Okay, so our takeaway here is that the limit as x approaches a is not affected by f of a. So f of a could be undefined, it could be defined. It could be a pole, it could be a vertical asymptote, it could be a point, right? But that's not going to affect the limit, right? We're going to have to look at the behavior nearby to see what happens to the limit. So there are 3 ways that limits do not exist. We've already talked about 2 of them. What's one of the ways that we said a limit doesn't exist? When what happens? Left and right hand limits are 2 different values, right? So that's 1. If the function increases or decreases without bound, that's another situation we already talked about, right? If it's going up forever as we get closer to that value or down forever. So that's what happens around vertical asymptotes, right? The function increases without bound or decreases without bound, okay? The last way that we don't see very often is if the function oscillates between 2 fixed values as we approach that value. So here is an example. Hold on. I forgot to write it down. I want to make sure I'm remembering the right function. Oops. I think I wrote it down wrong earlier. Okay. So this guy here if you try to find this limit, you draw the graph of this function. This is what it looks like. It's signed, so it's not surprising that it oscillates, right? But as you get close to 0, this is what happens. It just keeps going back and forth, back and forth, back and forth, back and forth, and then it spreads out as it gets further away from 0. Okay? So even if you pick numbers really, really close to 0, it's going to go back and forth between -1, -1, -1, +1, -1, -1, +1, -1, +1, -1, positive, over and over and over again as you get close to 0. It's never going to approach a value. Okay? So we don't see that very often, but in applications, you can see it a little bit more often than in just kind of basic calculus. So that's what it means to oscillate between 2 values. So in a table, so we're going to look at what it looks like to find a table of values for and kind of analyze the limit from there. So on Schoology, I posted a link to a Desmos that is here somewhere. That has a good visualization of limits, and it has like little dots that go around functions. So if you're having a hard time visualizing limits, check out that Desmos. But this last example I want to do together. So this says there's a mystery function that we can't see, but we're trying to find the limit as x approaches 3 from the right. So what would be some nice values for us to plug into this function to see what's happening as the function approaches 3 from the right? We can plug in 4. That's to the right. Does that tell us that the limit is 17? No? What's another value closer to 3? 3.1? Okay, 10.61. Can you still tell me what value that's approaching as we get closer? Because you pick a number. 2.5? 10. 10.5? Yeah, I guess it could get closer to 10.5, right? Because we're pretty close to 3, right? And we're at 10.61, but maybe it goes all the way down to 9. I don't know how fast it's going down. So how can we find out if it gets close? If it goes through 10 or 10.5, it gets or keeps going down. 3.001. What does it look like we're getting closer closer to? 10? What would be another number even closer so we can verify? 3.0000001. So what is my function getting closer to as we approach 3 from the right? 10, definitely, right? It's a lot more clear now that I picked values closer and closer and closer, yeah? So you do need to be able to find limits from tables like this, okay? Sometimes you'll have to pick the values. Sometimes the table will be there and you just have to analyze it, right? But it's the same thing that we're doing on the graph. So let's make our own table. For this, you can either use Desmos on your phone, or you can come grab a calculator in a second. I'm not going to make you make the whole table, but I'm going to have you in groups do it. So first, let's pick good numbers for our table together, okay? So if we want to find the limit as x approaches 0 of this function, this is going to be on the left. So what are some numbers close to 0 on the left that I could use? -1. I think we should actually go closer because we only have 3 spots. So let's pick some numbers really, really close. -0.1. We can even do -0.1 if you want. I guess that's pretty good. That's not terrible. And then what's one even closer between that to fill in that third spot? -0.001. That sounds good. How about numbers to the right of 0? Let's try to mirror it so it's about the same distance. 0.001, 0.01, and 0.1. That would work, right? Okay, rather than all of you plugging all of them in and finding the y values, I'm going to have you do it by table, okay? So you guys, 2 tables, do -0.1. You guys do -0.01. You guys do -0.001. You guys do 0.001. You guys do 0.01, and you guys can do 0.1. Okay? So you can either use Desmos on your phone or come grab a graphing calculator if you want, and plug in that value into your function. Round to 4 decimal places. Round to 4 decimal places. Yeah, just take one bus, please. Make sure you have the right number by comparing with your either tables or other people that have.
I got this for. Oh, yeah.
Oh, I lied. This one, the limit that's the weird oscillating one, if you want to change it, it's sine of 1 over x.
So basically 0. It's supposed to round like
Okay, 4 decimal places. Do we have a number for -0.1? What'd y'all get? 4 decimal places. 1.9487. 9487. So write it down if you didn't do this one. -0.01. I don't remember who did that one. Who did that one? You guys? What'd you get? 1.9950. How about negative 0.001s? What'd you get?
Yeah, sorry. 1.999.
Nice. So write down the ones that you don't have in your table. How about my 0.001s? Who did 0.001?
2.0004.
2.0004. How about my 0.01?
2.0050.
How about my 0.1? Who was that? Was that you guys? 2.0488. Okay, make sure you have that down. Now the left-hand side of that table is going to help us see what the limit as x approaches 0 from the left is. We'll call this f of x to make our lives a little bit easier. So what does it look like the function value is approaching? 2, right? We're getting closer and closer to the number 2. How about from the right as x approaches 0 from the right of f of x? On the right-hand side. As we get closer and closer, it looks like it's also approaching 2. So what does that tell us about the limit as x approaches 0 of this function? It exists and it equals 2. So if you had done a table of values for this one, which I'm sorry, I said sine of x over x. I didn't write it on my notes and I was brain farting. It's sine of 1 over x because it's undefined here at 0. And these numbers are getting really, really tiny as we come inside. So we get this oscillating behavior back and forth. So if you did a table for this one, it would be like 1, negative 1, 1, negative 1, or like 1, negative 0.9, 1, negative 0.9, 1, negative 0.9, right? And like you could oscillate and get closer. Like you could go negative 0.5, positive 0.5, negative 0.25, positive 0.25, negative 0.2, positive 0.2. And you can still get closer to 0. Like it can oscillate and approach 0 and still exist. But if it just consistently goes back and forth between the same values over and over again, it's not approaching a value, right? It's just going back and forth between the same values, okay? So that's limits from tables and graphs. That's what your homework is over tonight. But we're going to start section 1.2. To do that, I would like you to go ahead and try these limits on this graph here. And I'm going to add one more to this list. Remember, in order to check these limits, you need to look on the graph from the left and from the right and see if they're approaching the same value. So that limit will only exist if from the left and the right it's approaching the same value. Compare what you got with your table. And don't forget the fourth one that I added up there.
Okay.
You approach it from the right side, the right side and left side, if it's in the same place. And if it's in the same place, in this case.
Alright. No confidence in my answer. I'm having immediate confidence in my answer.
I can't see this.
The same.
I think these are points. So
All right, as x approaches -1, the limit is -1 because x approaches -1 from the right and from the left, the function approaches -1. Also, just a side note, what is the function value at -1? What is g at -1? It's also -1, right? So here it does happen to be the same as the limit. Is that necessary though? No. Does it really matter what this is? Whether the limit exists? No, right? But just a side note. Okay, limit as x approaches 4. Function is approaching 4 from both sides. What is g of 4? What is the function value there? So here it also happens to be the same as the limit. As we approach 5, switch colors here. Approaching 5 from the left and from the right. What is the function approaching? 5. What is g of 5? It also happens to be the same as the limit. Okay? And then this last one, as g approaches -5 from the left and from the right, what is the function approaching? 4. But what is g of -5? 1. Okay? So here, the limit is what is the function doing nearby? It's approaching 4, right? The function value itself is 1, right? So this is a case where the limit does not equal the function value, okay? Is there a value of x here where you would say the limit does not exist? What value of x would you say the limit does not exist? -3, right? They're going to infinity. Where else? 2. At 2, they're going opposite directions, right? This one's approaching 1, and this side is approaching 6. Okay, so I just told you a bit ago, and I've mentioned many, many times, does it matter what the function value is at the point? Does that determine anything about the limit, like whether it exists or not? No, okay? But for most of our functions, this happens. The function value and the limit do often end up being the same, right? We saw it 3 times on this graph. And I could find a lot more places on the graph where the function does equal the limit, okay? We will discover this way more in depth in a whole section called continuity. Because as long as the function is continuous at that point, the limit will equal the function value, okay? So most of the times, because most of our functions are continuous, the limit will equal the function value, okay? This helps us because what we're going to do next is we're going to evaluate limits algebraically. So I give you equations instead of graphs, right? And you're going to have to find the limit from the equation. Well, what's convenient is that most of the functions we look at are continuous functions, or they're continuous on their domains. And as long as the function is continuous, the function value will be the same as the limit, okay? So all you have to do in order to find the limit is find the function value. And we know how to find function values, right? For example, here, this is what kind of graph? A quadratic, right? Is that a continuous function? When I say continuous, I mean no vertical asymptotes and no holes, so no undefined values. So is that a continuous function? Yes, okay? It's a quadratic, okay? So any limit you want to find with this function, it's just going to be the same as the function value, okay? Because there's no holes, there's no weird things happening around it, okay? So, for example, if I want the limit as x approaches 3, I just need to figure out what is the function value at 3. How do I figure out what the function value is at 3? Plug it in, okay? So the first method you should always use when trying to find limits algebraically is always just try to plug it in. If you can plug it in and get an answer, that's the answer to the limit, okay? That's it. That's all it takes. It's going to be the first method. Now, granted, there's a lot of times where you're going to be able to plug in the number and it's not going to give you an answer because a lot of times we'll get undefined, right? And then we'll talk all the next couple days about what we do in those cases, okay? But the first strategy for evaluating limits algebraically is to just plug it in. It's called substitution, right? You're just going to find the function value. And this works for trigonometric functions, exponential functions, logarithmic functions, polynomials, anything that is continuous on their domain, right? So for any values, that function is defined. So the limit as x approaches 3 of this function then will just be 3 squared minus 3 times 3 plus 1. we're just going to plug it into the function, which is 1. So this limit is equal to 1. Is this function continuous? Meaning, are there any values where e to the x squared is undefined? Where is it undefined? If you plug in 0, you get e to the 0, which is 1. So that's okay. So undefined would be like denominators, right? Zeros in the denominators, or negatives in the square root, or negative log inside logarithms. Guys, so is there anywhere that's undefined? No, I can plug in any number I want. So that means that function's continuous, right? On its domain. It's defined for all values. So to find this limit, I'm just going to plug in 0. E to the 0 squared will be e to the 0. What's e to the 0? 1. So this limit is equal to 1. So algebraically, whenever you're finding limits, the first thing you're just going to do is just plug it in, right? And then you will know very quickly if that's not going to give you the answer, right? If it gives you the answer, then that's the answer to the limit, okay? Here, sine and cosine, are those both continuous functions? Yeah, do they have any holes or vertical asymptotes? No, so if you add them and multiply them together, you're still not going to have any undefined values, okay? So here we can plug it in. Sine squared of pi, or sine of pi is 0, so 0 squared is 0. Cosine of pi is negative 1. So this is negative 2. We'll remember how to graph piecewise functions and find those limits tomorrow because we're going to run out of time today. I didn't think we were going to make it there anyway. And they're not on homework today. Before you leave, come drop off your name tag on this table for me. I'll keep them for you. You can pick them up the next couple days. When you come in, make a pile of them. And if you borrowed calculators, if you don't mind putting them back,